Okay, it's the top of the hour. I think we can get started. Good day, everyone. My name is Jason McDowell, Chief System Integration Officer for the Energy Systems Integration Group. It's nice to see everyone here today heading into the first week of autumn, and would like to welcome our ESIG. Would like to welcome you to our ESIG monthly webinar for September. It's been a hot and brutal summer over the world, and it's been unprecedented heat, droughts, floods, and wildfires, which serve as a reminder to us the big job that we still have ahead of us. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials across the industry. ESIG also serves in a leadership role with the Global Power System Transformation Consortium, otherwise known as the GPST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and speed. ESIG leads the first of the 5 pillars, which drives the research agenda for the system operators. After our 2 topical workshops in Denver on forecasting and markets and long-term load forecasting in June, we continued our schedule of webinars and blogs during the summer, and we are now deep into the preparations for the fall technical workshop in San Diego at the end of October. I'm excited to share that we prepared another great lineup of tutorials and technical sessions, and I hope to see you there. Further information can be found at our website at esig.energy, where the final agenda and registration information are posted. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and if you think I think you'd be pleasantly surprised at the content. ESIG members will give you an opportunity to participate actively in all of our working groups and our task forces, and you can join us on the web at esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Before I hand it over to today's star of the show, I just wanted to share a few logistical items before we get started. First of all phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we're using Slido platform. If you have any questions, please go to slido.com and enter the code ESIG20. That's ESIG20 as the event code. The instructions are also at the bottom of this screen. Everyone will see a thumbs up button next to the questions to allow you to cast a vote and help prioritize the questions submitted. We'll plan to save about 10 minutes or so for the Q&A at the end, and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been saved and posted. We'll also plan to provide short responses to any unanswered questions after the webinar, so please feel free and encouraged to ask questions through Slido. Today's topic is going to be on interconnection requirements for grid-forming inverters. This is a topic of increasing interest and importance around the world, with over 1,300 registered for this webinar. With the energy transition from a system dominated by synchronous rotating machinery and wanting to transition to inverter-based resources. Here to talk about it with us today is Julia Matevosyan, the Chief Engineer of the Energy Systems Integration Group. Julia has over 20 years of experience in the electric power industry, with 10 years at ERCOT before joining ESIG 2 years ago. Julia is very active, leading industry activities across NERC, IEEE, SIGRE, and GPST, and is very well known for her work internationally. It is my great pleasure to welcome Julia here today. Today's webinar will take us on a whirlwind tour around the world for a look at what's happening at some of the leading system operators planning to install grid-forming equipment, including National Grid Electric System Operator in Great Britain, the Australian Energy Market Operator, AEMO, Fingrid, and ENTSO-E, and many others that are looking to integrate inverter-based resources with grid-forming controls. We'll also get an update on what's going on related to projects at NREL, NERC, and ERCOT in the US. And this webinar will cover capabilities sought from grid-forming inverter-based resources by system operators and compare various existing or proposed requirements on testing specifications. We greatly value the contributions that Julia has made to the industry, and ESIG, and also look forward to what she has to say. Just a short reminder once again that we will use Slido for questions at slido.com. The event code is ESIG20. And without further ado, let's go ahead and turn it over to Julia. Thank you, Julia.
All right. Thank you, Jason. Thanks for introductions. Let's go ahead and get started. Give me a second. Once the slides. Okay. So just in the order of kind of setting the scene and introduction, I have, and how do I get the pointer? In a second. Can you see the pointer?
There's an annotation button in the top right corner.
Yes, I got an arrow pointer. Laser pointer. Okay, can you see it on the screen?
Yes.
Okay, good. All right, so just to set the scene, I have this little cartoon here, and it should be perceived as a cartoon and not ultimate truth. But basically, consider this timeline where we are moving from strong grid dominated by synchronous generators towards weaker grid, maybe 100% IBR at some point, dominated by inverter-based resources. And so as we are moving along that timeline, we started with just very few inverters. There were very few requirements applied to those. Basically, they were supposed to get out as soon as something happening on the grid and not be on the way. As we progressed towards maybe 10-20%, then it was no longer acceptable, and requirements such as write-through got introduced, write-through voltage, write-through frequency events, and so resources stay connected. Then as we move forward to 20-50% of IBRs maybe, then we needed more functionality from inverter-based resources and asked for grid supporting functions such as frequency control and voltage control and dynamic voltage response, dynamic reactive response, sorry. And then so as we now progress towards 50-75% of inverter-based resources in some areas, we're already starting to get into some kind of constraints associated with weak grid issues, maybe in some more meshed areas that have a lot of inverter-based resources. These are also related to frequency and inertia issues. And so what is being done today is that conventional generation is kept online. So you'll see constraints such as we need to keep so many synchronous generators online to operate stably. Or additional equipment is being installed, such as addition of transmission lines to reduce electrical distance to stronger voltage source, or addition of synchronous condensers. And so in the absence of more advanced controls from inverter-based resources, there is either technical or economic limit of how much inverter-based resources can be integrated. So either it becomes prohibitively expensive with all additional equipment that we need to put in place to support higher shares of IBRs, or there is a technical limit and we cannot just go any further. And this percentages I have there, it's kind of for illustration. It's not to say that it's exactly this percent. Some systems can go further, some systems can go less, depends on the characteristics of the system as well. But also these measures that we are taking on today, like keeping conventional generation online, can lead to renewable curtailment, and it's expensive and time consuming. So I'll go to the next slide. So as we talk about advanced functionalities from inverter-based resources, we run into this broad term that we call it grid forming. And so grid forming controls, I pulled this definition from NERC white paper from 2021, and broadly grid forming controls are defined as controls that maintain internal voltage phasor constant or nearly constant in subtransient to transient time frame, and that allows inverter-based resource to immediately respond to changes in external system and maintain control stability during challenging network conditions. The voltage phasor must be controlled to maintain synchronism with other devices in the grid, and must regulate active and reactive power appropriately to support the grid. There are many variations of grid forming controls as well as grid following controls, and both of these types of controls are subject to physical equipment constraints, including voltage, current, and energy limits. There are also mechanical constraints on wind turbine generators. And then there is common understanding, as you will see as I'm going through requirements that have been established for grid forming resources, is that these performance requirements are in addition to what we currently have for grid following inverter-based resources. So potential use for grid forming control so far that we see is in weak grid, operation weak grid, damping of voltage frequency oscillations, response to phase jump, limit initial rock off. So you can see it as, supplementation or substitution of inertia. But basically the main idea is to limit rate of change of frequency after a disturbance event on the grid. Fast full current injection, subsynchronous control interactions mitigation, and black start in some cases. All right, so as we move towards higher inverter-based resources, we need to identify what our system needs. So as we progress towards this 70 to 80%, we need to know what are the system needs, identify advanced grid forming controls that we need for the system, and then produce and deploy inverter-based resources with these controls, and then disseminate lessons learned so we don't all have to reinvent the wheel each time and we can share. Also, I wanted to mention that deploying grid forming capabilities on inverter-based resources, and especially on battery storage, may be cheaper and faster than adding new transmission assets, because those require additional investment. This additional investment needs justification, and such projects take time. So as inverter-based resources, and specifically batteries, get integrated into the system, system operators may consider already today incentivizing or requiring some advanced controls from inverter-based resources so that they can kind of support their own development. All right, so a little bit of a history lesson. If we look at how requirements for inverter-based resources were developing so far, so this is for conventional grid following resources as we know them today. So it started around 2000s, where individual system operators that were seeing increase of inverter-based resources on their systems, they started developing additions to existing grid codes, or maybe new grid codes specific for wind initially, then adding solar and so on. So first harmonization efforts, you can see in 2007, where Nordic system operators in Scandinavia developed a common set of requirements that apply to the entire region. And also in Germany, system operators that operate in Germany produced a combined set of requirements that applied throughout. And then it again continued for a while with individual development of interconnection requirements until in 2016, ENTSO-E proved requirements for generators. So this is a common code that applies to all ENTSO-E countries and ENTSO-E systems. And they took effect in 2019. So these grid codes, they specify capabilities for generators that they must follow to interconnect to the grid. Diversity of grid codes that we've seen historically requires multiple product designs and increased equipment costs. Comprehensive harmonized codes took 20 years to develop in Europe, and in the US, there is still no harmonized grid code that applies to existing conventional inverter-based resources today. So there is a IEEE 2800 standard that have been approved in April last year, but it needs to be adopted to apply. And currently there are individual adoption efforts, but there is no kind of harmonized adoption for the entire US. And all of that, I'm trying to say that we don't have another 20 years to develop grid codes for grid forming inverter-based resources, because the pace of development of renewable resources and battery storage is so fast. We need to do it faster and do it now. All right, so just to go through a landscape of what is happening with grid forming specification requirements. So it's all started at the high level, where kind of people just looked at what functionality may be required from inverter-based resources going forward as we reach percentages higher than 75-80% of inverter-based resources on a given system. So there was a EU-funded project called Migrate that proposed this first functionalities that may be needed from inverter-based resources. And then Hawaii Electric Company, because they are smaller islands, they're facing rapid increase in renewable integration. They already in 2019 came out with high-level requirements for all new battery storage to be grid forming. And at that point, there were just 7 or 8 functionalities that they would require, and there were no more specifics on that. NREL Research Roadmap also identified functionalities that are important for future inverters, and same did a group that worked at ENTSO-E. And if you look at NRELs and ENTSO-E functionalities that they defined, they're pretty well aligned. VDE FNN guideline is from Germany, and it specifies, provides a guideline for grid forming behavior of HVDC systems and DC connected power park modules. So this is more of a testing guideline. So it has functional requirements, but also has some guidelines towards how they should be tested. National Grid, ESO, so the Independent System Operator in Great Britain, has developed a grid code change 137, which is a non-mandatory minimal specification required for provision of Great Britain's grid forming capability. So that was approved in the beginning of 2021. AEMO then followed with, it was kind of a white paper showing interest of AEMO in inverters with advanced capabilities, and kind of they plan going forward with deploying those. HECO then followed with more detailed requirements for grid forming batteries going forward. And so this time they had a little bit more specificity in the power purchase agreement, but also there was an additional document that describes tests, simulation tests that should be applied to validated model representative of a grid forming battery plant. And these tests would prove its grid forming capability. So that was the idea. EU-funded project Osmos, this is kind of a follow-up of a Migrate project, and they had very good work product that defines a grid forming capability, but also introduces new services that may be needed in the scarcity or absence of synchronous machines. DOE-funded project UNIFI has developed a specification for grid forming inverter-based resources, again, high-level functional specifications, and they released it in December 2022. National Grid ESO then supplemented the grid code change with the Great Britain Grid Forming Best Practice Guide. So this guide is basically an application guide to clarify how do you verify a performance of a grid forming resource in accordance with requirements that were introduced in GC 137. AEMO, just more recently, that just happened this summer, AEMO released the voluntary specification for grid forming inverters, and they are planning to follow up with testing requirements next. Fingrid developed their specific study requirements for grid energy storage systems, and this focuses on grid forming requirements for batteries currently going into weak grid areas. And I'll have example on that one. And then just fresh off the press, just happened 3 hours ago today, NERC, Inverter-Based Resource Performance Subcommittee, has developed this white paper with grid forming functional specifications for bulk power system connected energy storage systems. And this white paper just got approved by Reliability and Security Technical Subcommittee at NERC. So this is the highest subcommittee that approves white papers, guidelines, and standards. So this paper is no longer a draft. So as you probably heard from me talking through all the specifications at once, there are different flavors of the specifications. There are specifications coming from system operators or some kind of regulatory body. So I group them here in this table. And then there are specifications coming from research organizations. So this is kind of a first step to provide guidance to, say, system operators or transmission network owners in the area where they would like to follow up and develop specifications for grid forming resources. There are some drafts on the way. So ENTSO-E currently is working on the draft, which is a kind of update, grid code change to RFG. And that one has high-level grid forming specifications. NERC IRPS is no longer draft, so that moves up in this upper column here. And then there are planned specifications. So ERCOT is currently planning to produce specification for grid forming batteries, and Florida Power and Light is planning to do it as the next step. There are some working groups at SIGRE. There is a SIGRE working group that is focused on grid forming, and I can imagine they will produce specifications as well. UNIFI is going to update their specifications that they released last year, and Global Power System Transformation Consortium has a grid forming implementation council that focuses on streamlining deployment of grid forming technology, and I'm sure some specifications recommendation will come out of that as well. So if we talk about flavors of specifications, there are high level versus slightly more detailed functional specifications. I would say none of them is as detailed as current grid codes are, because this is still in early stages of development. And so technology is developing at the same time. And so there is no willingness to come up with very strict prescriptive requirements that will prompt the development of technology any further. There are functional specifications versus test-based specifications. So there are just set of tests that is defined, and the model is subject to a test. And if it passes certain criteria, then it's considered grid forming, and it's passing grid forming requirements. And then there are specifications that have both. Some specifications are split into core and advanced capabilities, where core capabilities are expected from all grid forming inverter-based resources, and advanced capabilities are maybe only several inverter-based resources in the area are supposed to comply with those. Some are not split like that. There are voluntary versus mandatory. Currently, mandatory is only HECO, and it's only with application to battery. All other specifications that are out there are voluntary. There are specifications that apply to all inverter-based resources and don't split it into requirements specific for wind or solar or battery. And there are more that are currently just focused on battery energy storage. And the reason for this, I think there are several reasons. In the US, focus on battery storage is because there is a lot of battery storage in the queue. If you look at the US-wide interconnection queue, and I have this chart, maybe hard to see here, but you can follow the link as very good analysis of interconnection queue in the US today. If you look at the how much storage is there, it's upwards of 650 gigawatts of storage in the interconnection queue. So that's not all of it will be built, but it's showing how much interest is there. And also grid forming capability is more straightforward to implement in storage, because grid forming capability requires some energy buffer, and that already kind of exists in storage. In solar, it's more there is another challenge that you need to have energy margin behind inverter to provide grid forming capability. And then for wind, it's even more difficult because it's associated with mechanical stress if a wind generator is providing grid forming capability. So I like this cartoon from Eckhart Whitman from Spring Technical Workshop in 2020. And it's basically to implement grid forming and energy storage is like teach kid to ride a bicycle, and then for solar it's like a monkey on the bicycle, and for wind it's like a bear on a bicycle. It can be figured out, but it comes at the cost, and maybe takes more time. All right, so let's move on to the next one. So if I look at common functionalities that are required, there will be some that are not in every requirement, some on this slide, I mean, that are not in every requirement, but overall, you'll see these common themes throughout all of the requirements. And I think it's a good sign. It's kind of that we're all high level at the same page of what is needed. And so these are basically response to voltage phase angle jump, a response to voltage magnitude step, response to change in sudden change in megawatts, so either load trip or generator trip, behavior at current limit. So this one is not specifically defined in some of the requirements. So some of them will say what's expected, and some of them don't have it. Counter imbalances and counter harmonics. Provide damping, load system strengths operation, islanded operation, and then black start. Black start, I have it separately in a different color, and I would like to stress out this. We always try to stress out this difference that not all grid forming are black start capable, but to be black start unit, you need to be grid forming. And so grid forming inverter-based resources have the advantages even without being black start capable, and they can provide improve stability of the system when system is all together and connected. But then you can also design inverter-based resources to be black start capable, but they need to be grid forming for that. All right, so I'll have some examples of kind of different types of codes for inverter-based or requirements for inverter-based resources. Just to give you an idea of kind of what's there. I don't have all of the specifications that I listed in here, but just wanted to show some of the kind of illustrative examples. And so I pulled this AEMO example, which I think is a good example of this high-level requirements not being too prescriptive, but kind of articulating what they're looking for. And they also have some simulation test results kind of to show what the behavior that they are looking for. So if you look at the document, you'll see that as well. So they're requiring nearly instantaneous reactive response to external voltage magnitude step. So this is this voltage magnitude step response, active power response to voltage phase angle step, response when inverter is at limit, and transition to and from limit condition must be smooth and stable. So that basically saying, not have any jerky behavior as you switch from operating at the limit to back to operating under limit. So this is as much as how behavior at the current limit is described. The behavior should not be detrimental to stability or to harmonic performance. Inertia response from grid forming inverters should be inherent, and so not waiting for measuring frequency and then responding, and then providing nearly instantaneous active power response to grid disturbance. So this is this response to megawatt loss. And then if inertia is configurable, it needs to be tuned based on network conditions, and then requirements for inertia constant maybe they may the high inertia constant may increase power oscillations and particularly be detrimental in strong grid systems. All right, so continuing on core requirements, so they have this surviving loss of last synchronous machine, and I'll come back to this more as I go through other requirements. So this is kind of a common theme associated with definition of grid forming capability. And this is not to say that a single grid forming inverter should be capable of maintaining stability in arbitrary island. This is rather that in a test that is dimensioned specifically for this grid forming resource under test, if you trip a last synchronous machine and it is dimensioned to support remaining load, it should stably do so and switch on and off, from being operated as island without synchronous generators to being operated back to together with a system that has synchronous generators on it. operate stably under low system strengths, and then provide positive damping to oscillations. And they have a list of oscillatory phenomena where they seeking help from inverter-based resources. In terms of additional capabilities, they define that maybe larger headroom, energy buffer would be helpful. Current capability above continuous rating could be helpful, and that speaks to low system strength operation, but maybe also island operation, and restoring grid from a blackout. That's where this higher continuous current capability may be helpful. Black start capability from some of the resources and power quality improvement. So AEMO underlines that these requirements are in addition to the core requirements, and maybe not all resources will be needed to provide that. Right, as we move to national grids requirements, you'll see that those are relatively similar to AEMO's requirements. So again, provide phase jump power, real inertia power. So that's kind of to the point of limiting rate of change of frequency after an event. Rock-off response power. So this is where they combine what they call real inertia power with control-based real droop power. And I have this in green is because also grid following inverters can provide this control-based droop power. So that's your fast frequency response or maybe primary frequency response. So these two responses combined are supposed to limit rate of change of frequency. Damp active power, voltage magnitude jump reactive power provision, and fast fault current injection, which is less than in a time frame less than 5 milliseconds. So again, you can see these common themes that I had on the first slide before I went into each of the specific requirements. They say if the unit is designated to be to have capability, then it is required to have grid forming capability. So again, underlying that not all units will be required to be black start capable and be over-dimensioned. Therefore, there is a minimum phase jump angle limit at which a grid forming inverter-based resource is not supposed to hit its current limits. And the recommended limit currently is 5 degrees. And then there is 60 degrees phase jump withstand capability that is specified. So that's basically like a right-through phase jump, where grid forming inverter-based resource is not supposed to disconnect. And I also wanted to say that national grids requirements slightly more detailed, but also most of the capabilities, they have to be announced by the inverter-based resource. So basically, they're not prescribed. You're supposed to have this much, I don't know, real inertia power, but you tell us how much real inertia power you have. And so there is a table that inverter-based resource is supposed to fill in to announce how much capability they have for each of these functional specifications. And then there is the rock-off power response is assessed for 1 hertz per second rock-off, but there is also rock-off withstand capability of 2 hertz per second. So that's basically right through for a rock-off event. And then there is also more details to definition of what's defined as real inertia power. Go to the next one. So as I mentioned, National Grid followed up and complemented the grid code change. And so this non-mandatory minimum requirements for grid forming with best practice guide. So this is a specification of recommended testing and verification to prove this grid forming capability. They already had a set of tests in the grid code that applies to currently grid following inverters. So all of these tests will apply to grid forming inverters as well. But then there are also additional tests to just verify grid forming capability. And there are in the best practice guide, they have then additional examples of testing active power rock-off response active rock-off response power under extreme events and full range of system frequencies, testing examples for active power phase jump, examples for active damping power, discussions of what it means with phase jump angle withstand value, and discussions on the tests of active power phase jump. All right. Fingrid, I see there are people putting questions in the chat. So as Ryan announced before, please go to slido.com and use ESIG 20 as a code, and then you can enter your question there. So we'll do Q&A from there. Thank you. All right, so now jumping to Fingrid. Fingrid is a mix of functional specifications and testing requirements all in one document. It's also, I think it's an interesting case there, because the way they introduce the specifications, it's more of a, for specific cases where inverter-based resources, battery storage inverter-based resources would like to build in weak grid areas. So they are saying in these areas, inverter-based resources cannot be built anymore because of stability limits. But if it's a grid forming resource that complies with these requirements, then they can build in this area. So that's how it's being implemented right now. So they also have this requirement to when grid forming inverter-based resource reaches its current limit, it should not switch to any kind of grid following mode and should operate at the limit, you know, and provide grid forming capability within the limits of equipment. It should continue providing grid forming operational characteristic even at highest and lowest state of charge. So there is a similar requirement specification in the NERC document as well. It shall provide autonomous near instantaneous frequency voltage support, maintaining nearly constant internal voltage phasor in subtransient time frame, and that means basically providing phase jump response, resisting change in voltage, and basically supporting system strengths. And then seamless transition between islanded conditions and grid-connected operation. And then again, they have requirement for damping and define frequency ranges where they're seeking provision of damping. Right, for voltage balancing, grid forming shall provide closed loop path for unbalanced currents to flow. There are additions to active power control and voltage control. So these additions clarify how current requirements that apply to inverters already with regards to voltage control and frequency control should be complied by a resource that is a grid forming resource. So it's basically describes how a provision between grid forming functions and then going into longer term providing frequency response and voltage support, how that operation is expected to be done. And then they have required simulation studies. So there is a table that lists disturbances to be tested, acceptance criteria, simulation software to test it in. So that basically points you towards whether it should be done a phasor domain simulation and EMT simulation is required. There are different battery storage operating scenarios that are described. There is prescribed state of charge from which you start testing, and then different P and Q output conditions pre-disturbance. The list also includes this loss of last synchronous generator test that I mentioned is also present in HECO's requirement, NERC paper, and in AEMO requirement. And additionally, they require hardware type test reports. And what's interesting, and I underlined here, I think that's the only example where I've seen so far, there are physical tests that are required. Maybe FNN has some physical tests as well. But this one too will have a physical test for phase jump and island operation where they will disconnect upstream 110 kV breaker and expect grid forming to support that part of the grid that got disconnected. and measurement of power quality, and they require monitoring period of 30 days after grid-forming battery becomes commercial.
Hi, Julie. We've
Right,
got
so-
about 20 minutes left, just to let you know. Thank you.
Yeah, that's great. I think I'll be able to wrap up in 5 to 7 minutes. So I wanted to bring up that the test of loss of last synchronous machine. I think there is, I see some confusion sometimes when we're talking about these tests, and people think, oh, you know, you need to dimension grid forming battery to support part of my grid, and it may be, you know, large part, maybe it requires a lot of over dimensioning. So that's not what it is about. It's just to test basically capability of a battery to be grid forming and operate without any synchronous machine and survive disconnection of a last synchronous machine. So this is a test that is applied to a model, grid forming inverter model. In the test setup, you have device under test is, for example, this 100 megawatt BESS. There is another same model that's connected that's half the size, a synchronous generator and the load. And the load is dimensioned such that under disconnection of the synchronous generator, these batteries are sufficient to support this load. So there is nothing strenuous from energy perspective or, you know, capacity perspective, and it's more to test grid forming capabilities in subtransient transient time frame. The reason why there are these two batteries is first to make sure that there is no control interaction between two grid forming resources connected in the same POI, and also that there is a proper power sharing that is happening once the synchronous generator is disconnected, and, you know, drop response is working as intended. And so there are these 3 tests that are applied. You trip synchronous last synchronous machines under 3 following conditions, where battery is initially discharging and ends up at a higher level of discharging when the synchronous generator trips. Then BESS is initially charging and it needs to switch over to discharging as a synchronous generator trips. And then if BESS is operating at its maximum active power, and then the synchronous generator trips, what happens then? And then the success criteria are stable initial conditions, no oscillations, all operating within limits. Voltage and frequency settle to stable and acceptable operating point within tolerance of drop and deadband. The oscillations are well damped, well-mannered recovery, and there are no excessive oscillations, and it's all settled. The waveform distortion dissipates and active and reactive power settles according to demand and draw characteristics of these batteries. So this is the test, and kind of, as I said, there is this similar trend that's happening, this test being in NERC white paper, in AEMO. In AEMO requirement, there is no test, there is just a requirement to survive loss of last synchronous machine, and I can imagine something test like this will follow in the testing specifications, and then Fingrid specifies a very similar test as this one. If we're talking about plant specifications, recently there have been notable events, IBR disturbance events you must have heard, specifically in the US, and NERC has released a number of reports. I think it's more than 10 now from 2016 up to now, where large amounts of inverter-based resources are tripping after a normally cleared fault, where they would be expected to ride through. So 2 of these events happened in Texas, from about a year, within a year from each other. So after that, ERCOT strongly focuses on improvement of inverter-based resource capabilities and performance, but also trying to strengthen the grid in this area, because both events happen in the weak grid area, propagated across very large distance, exactly, and far away from the fault. And that's exactly because this weak grid area and voltage drop propagates big distance. So they are looking at solutions. One of the solutions is adoption of IEEE 2800 write-through requirements. So these are more detailed, more stringent requirements than what ERCOT currently has. There is a recommendation to build synchronous condensers in this area to strengthen the grid. But also, on the other hand, if you look at ERCOT's interconnection queue, there are 17.5 gigawatts of committed batteries. So these are batteries with already signed interconnection agreements, and 2/3 of these batteries already have financial security posted. So it's fairly certain that, say, maybe 70% of this will get built. And if you look at the entire interconnection queue, there is 100 gigawatts of requests in ERCOT's interconnection queues for batteries. So ERCOT is looking at, is there any benefit of these batteries being grid forming? Some of these are going into very weak grid areas and can actually provide stability support in those areas. And so they conducted preliminary study on benefits of grid forming batteries in West Texas, and this study showed that while these batteries cannot solve all the issues, they can improve dynamic performance of the system in weak grid and support grid following resources that are connected there. And these are resource rich areas, so a lot of wind and solar is being built there. They still require proper control settings and coordinations to operate properly and stably. So as a next step, ERCOT is looking to develop grid forming requirements for batteries, including but not limited to performance requirements, models requirements, studies and verification. So that's kind of the first step. I think this first requirement that is being developed in the US. So as I mentioned, all of these requirements are voluntary. So the question is, how do these resources come up? How do they get deployed? Only HECO has this requirement as a requirement that applies to all batteries going forward. So in Great Britain, there was a stability pathfinder. I believe we had a webinar on this. This is a tendering process where National Grid looked to procure certain amount of system strengths and inertia, and in the second round, 2 grid forming batteries won. And so this, alongside synchronous condensers, and so these resources are supposed to comply with the GC 137 grid forming requirements. So this is one way to incentivize through tenders and procurement of certain amount of stability service, if you will, that you need in areas of in parts of the grid. National Grid now followed with development of stability market design. They have developed eligibility rules and contract structures and procurement strategies for future stability market and the midterm. So they have long-term, midterm, and short-term stability market, different lengths of contracts and different look-ahead time when the services are procured, but basically they expect midterm stability market, which is a year ahead and 1-year contracts to launch in 2023 still. In December 2022, Australian Renewable Energy Agency backed 8 grid-scale grid-forming batteries that were already in planning stages. And this is basically just a way to deploy this technology and get it piloted and learn more from multiple grid forming resources operating in the area. So it's not really incentivized by any kind of specifications or markets yet. AEMO has minimum system strength requirements in some parts of the grid. So you may think that would incentivize grid forming resources to come and provide system strengths. But I think the holdup there is that apart from contribution of fault current, there is no good metric yet that is widely being used to characterize system strengths support from inverter-based resources. And so I think that's where grid forming cannot show its capability, because it only can provide maybe 1.5 at best per unit short circuit current. And then, as I mentioned, Fingrid only allows grid forming resources to build in weak grid areas where otherwise inverter-based resources would not be allowed to build. ERCOT actually proposed similar idea to exclude from curtailment resources that are being built in weak grid areas and supporting system strengths in the dynamic study in 2018. Just wanted to mention that. So just in conclusion, if inverter-based resources are built with grid forming control, stability can be provided from a resource itself, and the need for additional mitigation from transmission assets is greatly reduced, and we can possibly achieve up to 100% inverter-based, and been shown in studies that is possible. Grid code requirements and market products are needed for grid forming inverter-based resources to be deployed in efficient and timely manner. It took 20 years to develop grid codes for existing grid following inverter-based resources, and we don't have 20 years to do the same for grid forming. There is a number of activities that's happening in the US and Europe and Australia that hopefully will accelerate deployment of grid forming inverter-based resources, and hopefully will lead to more harmonized specifications from get-go. And challenges are broad and global. There is much more work is needed and quickly to seize this window of opportunity with grid forming controls that we can deploy on batteries that are coming now, and they're being built very quickly, and so we need it today. So with that, thank you very much, and I'm looking forward to your questions.
Thank you, Julia. It's a great whirlwind tour of where we are today with grid forming requirements. If you have any questions, reminder again to go to slido.com and enter the code ESIG 20, ESIG 20. We've got about, oh my gosh, now about over 46 questions in the Slido, and with about 8 minutes left, we won't be able to get to all of them, but we'll get to as many as we can. First question, Julia, comes from Sivash. And this is a good question. It probably has many different perspectives, but if you were to pick the two most important functional specifications of grid forming inverters, what do you think those might be? Is it phase jump response? Is it inertial response? Maybe, answering from a system needs perspective. What do you think?
I think it's a loss of last synchronous machine test. That's so it's not a specific, I understand I'm answering not specification, I'm answering test. But I think that's a test that puts you through multiple specifications. So a test phase jump, it tests inertia and frequency support, whichever way you call it. So it tests capability for power sharing between multiple grid forming devices. So I think it puts you through a number of things at once. So if you can do that, you are grid forming.
Excellent. Thanks, Julia. There are actually several questions of the same flavor with the next one that's voted up. And they have to do with the extent of grid forming capability in various resources. So this question specifically asks, can you discuss to what extent a battery IBR versus a wind or solar IBR can be grid forming?
I think from control's perspective, there is no difference. So it's control is on the inverter, right? So each one of these can be grid forming, but then grid forming requires energy buffer to provide this phase jump response, to provide this people call inertial response or rock-off limitation functionality. And so for that there needs to be extra energy. So this extra energy in a battery is already there. For solar, you need to back up solar production. You need to keep margin. So that means you're losing revenue as you keep margin on solar. The same issue was with frequency response from solar. And for wind, additionally, it puts mechanical stress on drive terrain. So there are more considerations. So it's not only you are backing it off and you are losing revenue, but also you need to take into consideration that there is mechanical stress when providing grid forming capability. That being said, I mean, it's been tested in Scotland, and they've shown that it is possible. It's probably that OEMs will need more work and more research to understand how much heat the drive terrain takes and what it costs, and maybe price it accordingly. And then for, for both for solar and for wind, it's also, you need to weigh in revenue loss versus what are you getting for provision of grid forming capability. Whereas again, in battery, it's already there, and it's only a short-term story. So you may say, okay, so she's saying, battery is not losing revenue because it's using energy for grid forming capability, but we are just talking, milliseconds during subtransient, transient time frame when this energy is needed, but it needs to be there.
Yeah, thanks. Exactly. I totally agree, Julia. Dimitri has another question. This is one that we might be able to showcase some of the work done at ESIG. Dimitri asked, does ESIG have any recommended requirements for grid forming inverters to include intergeneration interconnection requirements? Maybe we can talk about some of the stuff going on with the reliability work activities.
Yeah, so I'd say, I mean, well, we had this report in March 2021 that summarizes requests, basically does what I just did, but at the time, and since then more specifications have been produced. I would say actually maybe NERC's white paper, so NERC Inverter-Based Resource Performance Subcommittee white paper would be the best, kind of the most recent resource right now where you can look at, because it makes recommendations of requirements, but it also in the appendix lists most of what I've talked about today. So you can find a lot of information there.
Yeah, great. Thanks, Julia. I'm going to combine the next couple of questions because I think they're similar regarding some of the grid services that might be able to be supplied by both grid forming and grid following IBRs, and wanted to get an opinion about adoption of IBRs and how they can be incentivized. I think you went through that a little bit. And there's another related question about that incentivization, around what the main barriers to widespread adoption of grid forming inverters are across the US. Is it technological, economic, regulatory, or standards? What do we think about the incentives and the barriers of grid forming?
Mm-hmm. Yeah, so to the first question, I think it applies both to grid forming and grid following. There are two ways to incentivize, right? Either you require as interconnection requirement. Of course, you need to prove the need for all resources going forward, or maybe even retroactively sometimes provide certain capabilities. And another way, if you only need a subset of resources to provide certain capabilities, then that can be done through some kind of either market or tenders, like National Grid is doing it, and so on. And so, I mean, just to take two examples, say ERCOT requires all inverter-based resources since probably 2008 for wind, 2012 for solar, to have frequency response capability in service and provide droop response if they have headroom. So it's not required to reserve headroom, but only if they have headroom, then provide. But then there is still a market for reserves, where resources that sell on this market and get awarded, they get paid, but they also need to keep headroom to participate in the market. So there are two ways to do it, and they can be complementary and depends on system needs. And then for grid forming and where the holdup is, I think, especially coming out from this NERC meeting where we took this white paper through, I think it's just this technology is new. We're still getting familiar with it. It will take a number of pilot projects. Nobody wants to be first. Everybody is looking for, somebody else to adopt. But even if somebody else overseas adopts, then we're still looking for somebody else in the US to do it first. And so I think this white paper approval is a good first step. Now we have recommendations for specifications. So now maybe Florida Power and Light, if they want to develop these specifications, they can pick up this paper and, use it as a guide, or ERCOT can use it as a guide. And so hopefully having this documents coming from research organizations, like those others I have listed in the table, that guides system operators to develop these specifications, and hopefully these are more harmonized if it comes from that point.
Great. Thanks, Julia. Well, we're at the top of the hour. I think we'll wrap it up there. There's plenty of other great questions that we'll try to get back to you on from here. There was one question about availability of the material, going forward after the webinar. And just as a reminder, we'll send out an email with a link to be provided once the video file has been posted on ESIG's website. So thanks again, Julia, for a great presentation. I want to thank you, also for the timely webinar and the timely topic. This is certainly something that's being discussed all over the world. As I mentioned earlier, the email will go out with the video file, and we'll answer some questions that we didn't get to. We really appreciate your engagement and look forward to seeing you again soon. And we have a joint ESIG and GPST webinar coming up next week on Tuesday, September 26th, where I'll be hosting Sten Arden-Stolze, the Senior Vice President of Engineering from Ørsted, talking about the GPST Grid Forming Technology Implementation Council, followed by our fall workshop at the end of October. Further information on all of our webinars and meetings can be found on our website at esig.energy under the Events tab, and all of our newsletters and informational emails. You're also invited to attend. Julia, thank you once again for a timely, informative webinar. We look forward to seeing you again in the near future. In the meantime, everyone take care, stay safe, and thanks for your participation. See you soon.
Thank you.